So, you're interviewing for a hardware engineering job. You know there's one topic that's almost guaranteed to come up: RISC-V. It's not just a buzzword, it's a huge shift in how we design processors. In this explainer, we're going to crack open everything you need to know to absolutely nail that interview. All right, let's do this.
We're going to start high level, what RISC-V even is and why you should care. Then we'll dive deep into the real nitty-gritty, the instructions, the hardware that runs them, and all the tricky problems you have to solve to make it fast. And then we'll tie it all together and show you how this knowledge is your ticket to landing that job.
All right, so first things first, what exactly is RISC? Well, put simply, it's a completely open source and free instruction set architecture. It came out of UC Berkeley back in 2010. Really, just think of it as the public blueprint for building a computer chip. Now, this slide gets at a really crucial idea. The ISA is a contract. It's the fundamental language that the hardware and software agree to use to talk to each other. For decades, the big ISAs, ARM and x86, were totally proprietary. They were locked down. RISC-V completely flips that on its head by making that contract open for anyone to use and build on, without paying a dime in royalties. This right here illustrates the whole philosophy behind RISC-V. It stands for Reduced Instruction Set Computing. So instead of having one super complex instruction that tries to do everything at once, that's CISC, you have a bunch of simple, lean, and fast instructions. Each one does exactly one job: load some data, multiply it, store it back. It seems like more steps, but it makes the hardware that runs it so much simpler and often a lot faster. So why is the entire industry jumping on this? Well, the perks are pretty huge. Being open and free is a massive economic win, obviously. But it's also modular, which means you can start with a tiny base and only add the features you actually need. This makes it perfect for building custom silicon, anything from a tiny microcontroller to a massive system on a chip. And that's exactly why you see these huge players like Alibaba and Western Digital already building their own high-performance RISC-V cores. Okay, so let's get a little more technical and talk about the ISA itself. We're going to move from the what to the how. Specifically, how these simple instructions are actually encoded into ones and zeros so the processor can understand them. Take a look at this. Every single RISC-V instruction, and I mean every one, fits neatly into one of these 6 formats. Each one is a 32-bit package, and it's broken up into these little fields like opcode, RD, RS1, and RS2. The opcode is the verb. It tells the CPU what to do. The other fields tell it where to get the data. This super rigid structure is what makes the hardware decoder so simple to build. Now, the main workspace for the CPU is something called the register file. It's got 32 general-purpose registers. And here is one of the most elegant design choices in the whole thing. Register X0 is always 0. You can't write to it. It's just hardwired to be 0. Now, that sounds almost too simple, right? But it's brilliant because it lets you create useful shortcuts, like a move operation, which is really just an add instruction with register X0. No extra hardware needed. So here's where it all comes together. An R-type instruction, like add, takes both of its inputs from other registers. But look at an I-type instruction, like load word. It uses a number, an immediate value, that's encoded right there in the instruction itself. And the S-type for store word does the same thing for writing out to memory. Each format is perfectly tailored for a specific kind of job. Okay, so we've covered the language, the ISA. Now let's talk about the actual physical machine that executes it. This is the Datapath, the collection of wires, multiplexers, and logic gates that brings those instructions to life. We're officially moving from the abstract blueprint to the concrete hardware. What you're looking at here is a basic single-cycle data path. The program counter, or PC, just points to the current instruction in memory. That instruction goes to the register file to grab its data. The data goes to the arithmetic logic unit, the ALU, to do the math, and the result either gets written back to the register file or used to access memory. Simple, but the whole thing takes one very long clock cycle to complete. But as you can imagine, that single-cycle design is pretty inefficient. So, to get more performance, we use a pipeline. It's just like a factory assembly line. We break the journey of an instruction into these 5 stages. By having different instructions in different stages all at the same time, we can finish one instruction almost every single clock cycle. It's a massive boost to throughput. And here it is. This is what that 5-stage pipeline looks like in hardware. You can literally see the stages laid out from left to right: instruction fetch, decode, execute, memory, and write back.
Data just flows through these stages, and those blocks in between are pipeline registers that hold the intermediate results. This basic design is the foundation of pretty much every modern processor.
Of course, no assembly line is perfect. You need a brain, the control unit, to direct all the traffic. And you've got to handle traffic jams, which, in the processor world, we call pipeline hazards.
So the control unit is just a big block of logic. It looks at the opcode of an instruction, and from that, it generates all the signals that tell the rest of the data path what to do. If you look at this little snippet of Verilog code, you can see how it works. It's really just a big case statement. If the opcode is this binary value, then set the control signals this way. It's a decoder, plain and simple.
Now, the biggest challenge with pipelines is the hazard. A hazard is just anything that forces the assembly line to stop. The most common one is a data hazard. That's when an instruction needs a result from a previous one that isn't finished yet. You also have control hazards, which happen when the processor hits a branch and doesn't know which instruction to grab next.
And this slide shows us how we fix a data hazard. On the left, you see the pipeline has to stall. We have to insert these bubbles, which are just wasted clock cycles, while one instruction waits for another. But on the right, we use a trick called data forwarding. We literally add a wire, an express lane, to send the result from the ALU's output right back to its input. That way, the next instruction can get the data it needs immediately, and the stall is completely eliminated.
Okay, we've gone through a ton of technical detail, but let's bring this all back home. How does this help you prove you know your stuff in a hardware design interview? Interviewers aren't just looking for textbook definitions. They want to see that you can connect the dots. Can you explain why the I-type instruction format means you need a sign extension unit in your data path? Can you talk about the trade-offs of using data forwarding versus just letting the pipeline stall? This is the depth of understanding that really sets a great candidate apart from a good one.
And you can back up your knowledge with real-world data. CoreMark is a standard industry benchmark for processor performance. This chart shows how a well-optimized RISC-V core can actually achieve a higher score, meaning it gets more work done per clock cycle than other popular open-source designs. This proves that all those microarchitecture details we just covered really matter.
This quote from the RISC-V community online really just sums up how versatile it is. Whether you're designing a custom chip from scratch, programming an FPGA, or even building a software emulator, these principles are exactly the same. It's become a universal language for processor design.
All right, so as we wrap up, let's distill all of this down into the key things you absolutely need to take with you. Just remember these 4 things. RISC-V's power comes from its simple, clean foundation. Its modularity lets you build exactly the processor you need, nothing more, nothing less. Its openness is what empowers innovation. And maybe the most important part, it's accessible. You can go download an open source core right now and start playing with it. You know, the beauty of RISC-V is that it's not just a theory in a textbook. It's a toolbox. It gives you the fundamental building blocks of modern computing and just invites you to create something new with them. So the final question really isn't for an interview, it's for your career. You have the blueprint. What will you build?